Force fields are fields that exist in regions of space, and it's nature's way to push or pull on something without touching it, okay? And to help you guys understand an electric field, we're going to compare it to a gravitational field. Why? Because you live in a gravitational field and it's easier to picture. Okay, you know that if you let go of your keys, what happens? Duh, they what? They fall. How does that happen? You know what's weird? We actually still don't know how gravity works. Isn't that weird? Okay? You know that guy with the really bad hair, E equals mc squared? We talking about? Einstein. Up into his deathbed, Einstein was still trying to figure out how does gravity work. And Einstein didn't figure it out yet. Okay? So one theory is there's this thing called a graviton. It's like a particle, whatever. We still don't know. But we can describe gravity really well. Okay? So here's how gravity works. Gravity acts on anything that has mass. Okay? Mass. So mass is just measured in kilograms. Anything that has a substance there, an atomic structure there, gravity is going to pull on it. The strength depends on the amount of mass present and then 1 over the distance squared. So what does that mean? It means that the more massive your planet, the stronger the gravitational field. Okay? So for example, where is gravity stronger? Anyone know? On Earth or on the moon? On Earth, okay? In fact, that's one of the first things we did. When we put a man on the moon, Apollo missions, one of the first jobs for the astronauts was to measure gravity on the moon. It's about 6 times less. So hopefully in your lifetime, space tourism is going to take off already. There's this crazy guy in Arizona building a spaceport. You can buy a ticket to go fly in like 2018 or whatever for like $200,000 or whatever. I don't know. So, you know, yeah, a little pricey, but eventually, hopefully, they can get that price down. But one day, maybe go to the moon, and it'd be really cool. On the moon, everybody can slam dunk a basketball, jump over, I don't know, 10-foot pole, whatever, yeah? Okay? Everyone's Superman on the moon. It's gravity 6 times less. It's awesome, okay? But the other factor is distance squared. So what does that mean? If you are twice as far from the planet Earth, you know what's weird? Gravity's stronger or weaker as you get further away. It's weaker. It's how much weaker, though? What's 2 squared? It's 4. It's 4 times weaker. It's an inverse squared relationship. And the way you can think about it is if you move one object twice as far from another object, well, the other object now is also twice as far away. It's called the inverse square law. Gravity is only attractive. What does that mean? Gravity only will pull you down, okay? It doesn't push you up into the sky. So later on, when we study sports physics, a common mistake is sometimes people make gravity positive 9.8 meters per second squared instead of negative 9.8 on the planet Earth. So what that means is if you're playing basketball and you take a shot, suddenly like your basketball gets sucked into the sky. It's bizarre, okay? So don't mess up your math there. The other thing weird about gravity is as far as we know, you can't block gravity. You can't shield it. If you can figure that out, that means you probably figured out how gravity works. Come see me. I will become your agent. You can quit all jobs that you have. I will too, because you'll probably get like the Nobel Prize and get all these patents and invent anti-gravity paint and have flying cars and shoes and whatever, right? Okay? And then the other thing that's weird is you can store energy in a gravitational field. Okay? That's actually a huge idea when we study roller coaster physics, and it's our big theme for the end of the year. Okay? Anybody know how like the Raging Bull, Batman, Demon, the American Eagle, how do all those roller coasters work? You got a box with wheels, okay? There's a motor that pulls you to the top, but once that motor lets go and you go down that first hill, okay, yeah, it's gravitationally powered. There is no motor inside a roller coaster, which is exactly why we go on Physics Day in May. It's perfect. It's a multi-million-dollar energy lab, okay? So you don't pay for gravity. That's stupid. Gravity's free with your subscription to the planet Earth. Welcome, we come in peace. But what you pay for is the energy it takes to lift the coaster to the top of the track, and also a way to fall and not die through corkscrews, boomerang loops, etc. Okay? Electrical fields. Okay? Notice there's an analogy. You can kind of compare the two to help you see what's going on. Okay? Electrical fields don't act on masses, they act on electrical charges. So how about this? My keys right now. True or false? There are no charges in my keys. The answer is what? False. There are charges. But how come I'm not getting shocked by my keys? Why not? If there's 50 billion protons, there's what? 50 billion electrons. It's electrically neutral. So the other thing that happens is the electric fields cancel out. A positive charge, turns out it has a repulsive field. A negative charge has an attractive field. The net field is it cancels out. Okay? But here's what's interesting. Okay? If you compare the two, you can kind of see how gravity is similar to electricity. It helps you kind of understand it better. An electrical field acts on charges, so the strength of it depends on the amount of charge present, okay? So you guys have seen these like plasma ball toys. They're a lot of fun. You can get them like at a hobby shop store now. They used to be really expensive. Now I think I've seen them as cheap as like 20 bucks in the mall, okay? So these things are awesome. They're designed to not really shock you because you don't want anyone to get hurt. And all it is you have a electrified source in the middle. There's an electrode. And then the outer part of the sphere, they coat it with like a neon type substance. And there's some kind of like argon gas there that's safe. So that when you touch it, you provide a path for the charge to flow to ground. But it helps you see the electric field, okay? That's what I like about these. Now if you think about it, if I have twice as much charge in the center here, then the field's going to be what? Twice as strong, okay? But the big idea is to help you realize the inverse square law. So practically speaking, we're not really focusing a ton on the electrostatic math in this unit. It's more the ideas that count. So if you're outside and a thundercloud comes in over your head, and let's say you're a tall guy, like Evan, you're really tall there. If you are twice as tall as anybody around you, the thundercloud will not be twice as much attracted to your head. It'll be what? It'll be 4 times because it's the inverse of the square. If you're twice as close, it's 4 times as straight. Conversely, if you squat down so that the person next to you is twice as tall, now they're going to be 4 times more likely to be struck, etc. Okay? Now the weird thing about electricity that's cool is not only can you attract, have an attractive field, you can also what? Repel, right? And that's huge. So what's the rule of thumb? Opposites will what? Attract. So positive proton will attract a negatively charged electron, but then likes will what? Repel there, okay? The other thing that's kind of cool is you can actually shield an electric field. You can actually block yourself from a field there, okay? That's called electric shielding. Next week, like, I don't know, Tuesday or Wednesday, we're going to prove it to you. And actually, I can't take credit. It's a student who came up with the experiment. We're actually going to get out a giant metal dog cage. And don't worry, it's been cleaned out and all that. And we'll take a volunteer. Whoever goes in the dog cage, you're the safest person because I'll try to attack you with the Tesla coil, the Van de Graaff generator, and you're perfectly shielded. So what's cool is you can actually shield yourself from an electric field there. And then the last idea is you can store energy, and that's huge. All of modern life is we can store up energy in an electric field, in a battery, in a power station, etc. there. Okay? Moving on in terms of our electric fields, okay? Definition of an electric field. The equation is E, which is for electric field, is equal to F, which is force, divided by Q, which is charge, okay? An electric field is a force vector that surrounds the space around a charge, and it's a force field, rather, that acts on other charges. And by definition, we use a positive test charge, a hockey puck, so to say there, okay? So a good way to see that is the last little simulation that you guys tried yesterday there. So if you recall, the test charge we're going to use is this little positive hockey puck there. And if we want to visualize the field there, you can see that the field is defined by this positive test charge. We could have defined it by negative test charge, but usually, mathematically, we like to define things from a positive reference frame. Okay? So a positive source will always have a repulsive field. How about a negative source? A negative source will have a, what kind of field? Attractive field. You see that? It's as simple as that there. Okay? That's just how we... The next thing to notice is, see this little arrow on top? Okay? Your book, sometimes you'll see an arrow on top of E and F, or you'll see it in bold. Okay? And what that is it's called a vector. What's a vector? It has both the size and direction. So for example, an electric field could be 10 newtons per coulomb to the north. Okay? What does that mean? It means that if you have a charge in that field, it'll be pushed northwards 10 newtons for every coulomb of charge, etc. Okay? Versus going down 10 newtons per coulomb south or east or west there. Okay? So mathematically, it's not that hard to calculate. It's just literally how much force do you put on a test charge inside that field there. Okay? And in real life, usually you don't worry about it because somebody did the calculation for you. But if you want to make a touch screen respond to your finger's touch, you got to make sure the electric field's strong enough to register that touch, but not too strong because then you're wasting the battery. Something like that there. Okay? Or how about a Xerox machine? Anybody know how you get a Xerox machine to stick ink toner to a piece of paper? You literally do what? If you charge up the paper, let's say negative, then you can charge the ink what? Positive. Then you put it in an electric field to push the ink onto the paper there, right? And if it's not strong enough, it's not going to stick. That's when it looks all kind of splotchy. Okay? So I don't know if you guys have a laser printer at home. One little thing you can do to try to fix it is you pull it out, the toner cartridge, you shake it up, and then there's usually like a wire that generates electric field. There's usually like a little brush that comes with your printer that you brush it off to clean it off, and then usually that helps there. Okay? It's kind of nerdy. No biggie. Questions so far? Any questions? Okay. To visualize what a field looks like, the rule of thumb is you have to use a test charge. And by definition, we use a positive test charge. Okay? Then what you do is you kind of probe the field at different points, and you determine which way the force is going. And then if you connect all those force vector lines, then you know what the field looks like. So for a positive source, if I have a test charge here, it's going to be pushed away, right? And the closer I am to the source, the stronger the force is, so I draw a bigger arrow. If I connect all those arrows, I'll get the final field line there. Okay? So remember this toy, our little fun fly stick here? Okay? Suppose that it's a positive source, okay? It really doesn't matter what it is. And then this is my test charge. So right now, it's not going to feel a force because there's no source of charge. So I have to charge it up by pushing the button. If I put some charge then on my Mylar here, it'll pick up that charge. Oh, and it just whacked me in the nose there. There you go. And it'll have a net charge there, right? And so here you can see then it's a repulsive field because like charges will repel, right? And it's going to push it away until it hits the wall there because it polarizes and induces the charge in the wall there. Okay? So anyway, that's how we try to visualize our source of charge there. Next, let's keep this moving. In terms of drawing electric fields, the rules are real simple. Lines begin and end on charges. They extend out to infinity, theoretically. It's just they get infinitely weak, and then they never cross. Okay? How come you can't have field lines cross? The reason why is if they cross, you wouldn't know which way the force is really going. Okay? Next, the rule of thumb is you always flow away from a positive source and towards a negative. Larger charges of source means you're going to have more field lines. If you get more field lines, there's a higher density. That's how you can tell the strength. And then if you have more than one source, you get what's called the vector sum. Okay? So for example, if I have a positive source and a negative source, like down here, what's going to happen is the positive test charge will flow away from the positive and towards the negative there. So if I pick a point out here, we can actually figure out what's going on by combining the two fields, and the net result is called the vector sum. Okay? And we're going to do a little worksheet tomorrow to help you figure that out there. Okay? But as an example, let's take a look at one of the sims you guys did yesterday. Okay? If you look at having multiple point charges, the field is more complicated. Okay? Because a negative one's real simple. It's a black hole. A positive one is like a hill where the charge flows away. But let's try looking at our simulation from yesterday here. Okay? So if you look at our little electrostatic simulation, a cool way to visualize a positive source is it's like a giant hill. So the positive test charges flow away. It's like a hockey puck there. Okay? It's pushing it away there. A negative source is like a black hole. It attracts all the charges in there. Okay? Now in real life, you never just have a single charge by itself. You usually have a complex system. So for example, a dipole is a common system here. Okay? What's in the word dipole? Anyone know? Di means two. Okay? So in real life, wait for the lunch bell to go. Okay? Like a battery, you usually have a positive side to your battery and a negative side. Okay? The point of doing that is you set up a super strong electric field. Where's the electric field going to be strongest? Like way out here on the edges? Or in between the two. Exactly. In between the two. Because here we have a repulsive field from the positive source, the positive end of a battery. And then we have a negative field from the negative terminal, an attractive source there, right? So in between, you're going to have a super strong field. Think of it like you're on a like a sled or something, right? You're going to go really fast in the middle there. You see that? And we can figure out what these field lines look like by applying the electric field rules and visualizing each field on its own and then just adding them up together. Okay? So in a nutshell, okay, today what we're trying to look at is defining what an electric field is. It is a force field that surrounds a source of charge, and anytime you have a source of charge, the space around it changes. Okay? And you can exert a force on there. And all of modern life is how do you move an electron from one point to another, but not just randomly, okay? To do cool stuff, right? Like send a message, a text message on your cell phone. Make sure that your clocks keep time accurately, right? Surf the internet, all that good stuff there. Okay? So in a nutshell, electric fields are part of nature, and it's a way to put a force on an object at a distance without touching. And gravity, electric fields, are probably the most practical examples you'll see in day-to-day life. Okay? So, electric field.